So today I'm going to try a really fun and simple experiment. I'm going to lay down on the sidewalk and try and fall asleep, and then I'm going to suddenly get up and start running while I've got my electrodes, ECG, connected to my heart monitor recording the data, and I also got the camera in my eyeglasses recording the video, and we'll be able to see and understand the relationship between what's happening around me and what my heart's doing, what's happening in the body and around the body. So get this sudden upchirp effect, and we'll be able to apply the chirplet transform to analyze that data. So it'll start out kind of slow. It's going to sound like and go higher in pitch. So let's get started. So there's 5 steps to doing a good electrocardiogram. The first step is to shave. Start with a beard trimmer first, if it's long, and then a regular shaver. The second step is to shower, body scrub. The third step is sandpaper. Something nice, like a nice fine sandpaper, even works pretty good. There's a couple of different grit numbers here. Sandpaper. And the third step is isopropyl alcohol. And the fifth step is the electrodes themselves. And then of course you put on the heart monitor after that. If you shave regularly, you probably don't need the beard trimmer. Sometimes I reference over on the left leg, right arm, left arm area, and then of course the 4th and 5th intercostal regions. A little bit of sandpaper, and this here is a number 320. I think that'll be about right. One spot is here, the other spot is right up here. I just put a little mark there roughly where the spot's going to be. And the date and time are there. And so now what I'm going to do is I'm going to push the magic button on here, and the lights will come on and we'll know when that is. So now I've got it in the pipe, and I'm going to tighten the pipe fitting. Keep the water out. So then my heart monitor's inside this pipe, and if I've got the heart monitor in the pipe, pipe can keep water in. It can also probably keep water out. And I'll run and swim with this thing on. That's pipe fittings attached to me, and then I've got these 4 wires here that say R. It goes here, driven right leg, and G will be the other side. And 1 and 2, and G will be here, and then it doesn't matter what 1 and 2 are, but I'll usually just conventionally consider 1 to be the positive lead, which will be over here on this side. So this is 1 right here. I'm going to call this 1, and so now I've got here, there's a clock there on the screen, and I'll push F12 to get it to full screen, and then I can put that down here so I can see that clock, and then this clock, I guess if we just lean that up here like this, it'll be, and then I got to get my screwdriver.
Yeah, well, at least not with the Android
Huh.
Weird.
That's funny, because a clock should be able to be a clock, you know?
There's probably a setting.
Yeah, you can always download an app for that. It's just a question of how easy these things are.
Yeah.
Whether it's super easy.
No, they have a setting that basically says display time with seconds.
Oh, yeah.
So it's just
There it is. Okay, that's good. So now we can see what time it is
pretty synchronous.
according to these clocks. So that's 31, 32. Yeah, so they're pretty close. Those two clocks are pretty close. And then I'll undo this pipe here. Open up this this pipe here. And it's flashing, so I can see here the clock.
Yep.
And that clock over there. And then if I push it somehow so that I can see it, because that'll stop it.
Yep.
And then so we're going to look at some of this ECG data here, and data that we collected last day. And so I've written a short little Octave script. So we're using a program called Octave, and this is the script that reads the data. So it takes in this data EXG15 from Wednesday, March 10th, run swim, where I was laying down. And then I suddenly got up and started running. I read the data, and now when I put those ECG electrodes on, there's a certain time I started the data recorder and then put the electrodes on, so there's a lot of noise in the data. So for channel 1, the first 66,019 points are bad, or garbage, and 66,020 is when I connected the left electrode. And the right electrode, I connected that at the first 77389 data points are bad. So 70,390 onward samples are good. So because one of the channels is bad from this point, we're going to start the data record when both channels are good, so that they're in line. So that's a loss of about, less than 3.6% of the data is bad at the beginning when I turned the apparatus on and then put the electrodes on. So there's approximately, this is about 1.8 million samples of good data. The swim was around the millionth sample of the good data. These are just comments. When you start something with a % sign, that's just a comment in the file. So what I do is I go F equals F open, in quotes, ECG data, the file name, and then it'll return me a file handle, which is just a number, an integer. It starts at 3, and when I ran it, F was equal to 19 or whatever, some number, depending on how many times you've opened a file. A is F read, that's a formatted read of F, the file handle, so that's just the number. So if F open here returns a number like 19, and you go A equals F read of bracket 19, comma, quote, UCAR, unquote, unbracket. It will return the data into an array A, or data element A, and the semicolon at the end just stops it from printing, so it doesn't show up on your screen. And then we reshape that data to A, comma, 16, and length of A over 16. So it reads in as a one-dimensional array, but I really want to understand it as a two-dimensional array, so I'm reshaping it as a 2D array. And this channel 1 is 256 cubed times B, the fourth column, plus 256 squared times the third column, plus 256 raised to the 1, which is just 256, times the second column plus 256 raised to the 0, which is just 1 times the first column. And that's just the order the data comes in. Channel 2 is likewise the 8th, 7th, 6th, and 5th column. So columns 1, these are byte columns, 1 through 4 are the bytes of the channel 1, and columns 5 through 8 are the bytes of channel 2, and the ordering in terms of the significance is that the higher columns are more significant. And so this is just giving us channel 1 and 2. And our ECG signal, which I'm taking, is channel 1 minus channel 2. And we saw earlier the electrode placement. There's a picture there that shows where the electrodes are placed. And one of them is a little bit, to the left here, and the other one is up and to the right. And those placements were advised by my doctor. Actually gave me a recommendation in a video call of exactly where to place the electrodes to get the most meaningful electrocardiographic signal. Not necessarily the strongest signal, but the most clinically relevant signal. So now we're going to remove not the first 66,019 data points of garbage. We're actually going to remove the first 70,389 points of garbage, because we want to remove the garbage from both. We want to start the data record at the time when both channels are good. So channel 1 is equal to channel 1 of S. This is the start index, 70,390 to length of channel 1, semicolon, so it doesn't print. And then channel 2 is equal to channel 2 of S to length of C2. And then now I'm taking the electrocardiographic information. E is C1 minus C2. CLF clears the figure. It used to be CLG, but CLG is no longer used as a command, so now in modern day the command is CLF to clear the figure. Now what I noticed is that 200,000 data points is about the most you can plot in a graph and still see a recognizable electrocardiographic waveform, and have it still look like an ECG waveform where you can see the little spikes in the waveform. So I prefer not to to plot a graph of only 200,000 points. And it so happens that we've got about a little over 1.8 million points. So that gives us, if we do subplots, we can do 9 rows of data and still see each of the ECG waveforms quite clearly. So this will plot out 9 rows of 200,000 records in each row. So now the command to use, and I'm in this directory, I'm in a directory swimop 2021 March 10th. I call these swim ops. A swim op is OP stands for Ontario Place, so swim at Ontario Place. That's where I like to run to swim at the beach there. So usually I have my data records. This is my daily exercise routine, and I try to get out for my daily exercise for health. And so it consists of a run and a swim. So in this case I'm laying down and then I get up and run really hard and then swim hard and then come back fairly slow and easy. So it'll be a hard run to the beach, a fairly hard swim, and then an easy trip back. So the heart rate will be less going back after the swim. And then now if you look at the data, if we go Octave, and usually I don't like the GUI. I'm not a big fan of GUI, -- no GUI. And then we can go ECG, read data, and it'll come in and it'll create a plot here. And then if we wish, we can take that plot here and we can take that plot and enlarge it here a little bit. And sometimes if I run it again, it'll run it nicer in terms of reshaping. So now I can see the data here very, very clearly. I can see this is when I'm sort of laying down, relaxing, and then I get up and I run hard. You'll see when I stretch out that data and look at it more closely, you can see that it is starting out slow and speeding up. And then you can see it here, and then this is where the swim occurs right here. You can see that jump. The swim goes here, and then you can see that the data is kind of crummier or noisier when I'm going the swim because the water affects the electrodes. And then you continue over here. One way I find it's nice to be able to, the human ear is very attuned to frequency and sound and audio. So one thing I can do is I can play back that record, and we can listen to that whole record to understand what it sounds like. So if I look at, when you're inside Octave, you can type, I wrote a little script here that is E here, and I had it originally as a function, but I commented out the function because Octave interrupts it. It gives a warning and exits. So ES is the variable that we assume that E in. So ES is the variable, the scaled version of E. E is the ECG data, and ES is scaled. So I've gone ES equals ES minus the minimum value, and ES equals ES over max. So that goes from 0 to 1 on the interval, and then I've just doubled it and subtracted 1 to make it go from -1 to 1, which is the range of which the audio player plays best. So you can see when we play a sound, we want to play it with the on the interval from -1 to 1. So just to understand how this audio scaling works, let's say I'll make some variable like, I'll say a time axis, time equals 0 to 44/100 minus 1 over 44/100. So that's just a time index from 0 to 1 second. So let's say I'm going to let y equal cos 2 pi times 1000 t, and then we're going to go going to listen to that sound, and you can see that's just a cos wave, and then it'll stop. I'm at about a quarter of the sample rate. Now if I control Z out of that, I'll VI this file here. I had this set to reduce sampling rate, so let me go back to the normal sampling rate 4410. I had it set to a quarter of the sampling rate, and then so there's 1000 cycles per second tone, and you can see, just I want to give you an idea of what happens if it's out of range. So if I'll just go here, player equals audio player, and then I'll play player. That's basically what it's doing. Now my sound level's pretty normal. If I play that louder or stronger, like if I go y equals 10 times y, say that's stronger, and then I'll go player ES equals y and play that, you can see it doesn't sound at all like a 1000 cycles sine wave. It's much distorted because it's clipping, it's too strong. So if you plot that waveform, of course you can, there it is right there. I'll go CLF to clear it because it's in the last subplot of the 9 plots, and then I'm going to go plot Y again. And so there it is. It goes from -10 to +10, and it's just simply too strong of an amplitude. So that's why we need to scale it. So that's why that little script I wrote scales the function. So now if I go ES equals Y, and then it sounds normal again because I've scaled it properly. So now let's go ES equals E, this is the ECG waveform, and let's listen to that. So that's about 2 hours. That data record is about 2 hours, 1 minute and 2 seconds long. So let's come back inside here because I think we can hear it a little bit better inside. There's a little less traffic noise. We'll listen to that again. That's the swim. We can hear the noise there. And so you can hear at the beginning, at least, very distinctly, the part of it that's laying down and then speeding up. So let's just listen to the first little bit. Say 1 to 200,000 points. And so that's not the part that chirped. So let's say 200,000 to 400,000. So that is the part with the chirp in it. Let's narrow that interval down a little bit. So that's the part that has the chirp in it. And we can try to isolate or identify the part that has that chirpiness in it when I suddenly got up. Let's try 25. Not quite. So 25,000 to 28,000 or something. So that's got the chirp in it right there, maybe 20. So you can hear clearly that that's the part of the signal that has the chirp in it. We can try to narrow that down a little bit. Maybe. And so that's roughly the part that has the chirp in it. And so we can identify or isolate the part that has the chirp in it, and then we can try and plot that. So just to make the numbers nice, let's say I'll make this 24,501. And then now let's plot ES, and we can distinctly see that chirp there. And maybe what I'll do is I'll make this window a little bit smaller. I'll just resize that window to the point where it's about the right size. I want to resize this window as well. So I've got the two windows, one above the other, and then I can see the plot. And then, so that's the plot there. And you can see that chirp. You can see they're spaced out quite far apart over here, and they get closer and closer together here. And we can probably tighten that just a little bit. So let's go say start equals 248001, whatever it is. And then we'll pick a start value, S to S plus 4999, say 5,000 points. That's too little. See. So there's 20,000 points. I think we can hear that pretty clearly. And then I'll go plot. So you can see that right there. You can see that pattern there. And as we narrow that range down more and more, we can kind of identify the part of it that has the chirp in it. Okay, so now I'm just going to resize this window, and I want to look at, change the shape of the plot window a little bit. So I've got a plot window here I can recognize and see things in. Now what I want to do is use TF. TF is a short little script that I wrote back in 1990, and this computes the sliding window Fourier Transform time frequency. Let me close that window and go back to this one. Just got larger font here. It's harder to see the help file. Most of those help files I wrote were for 80 characters wide, but I've got a larger font, so it's a little bit easier to see here. So now let's go A, some matrix A, or say E equals TF of E. That's the time frequency. And you'll see it'll just give me a two-dimensional array. And it tries to figure out the optimum size of the array. And then if we try to display the array E is an array of complex valued quantities. So if we try to display E, it's, complex valued. So one thing we can do is look at the magnitude of E, and it's hard to see, of course, very much there. So what I tend to want to do is look at it on a log scale, log of this plus some small number epsilon. And now we can see, the time frequency analysis roughly. And we can kind of see, depending on what we set epsilon to be, like if I set that to be 1 instead of epsilon, it'll look pretty similar. Set it to be 100. And you can see it takes away detail in the dark areas of the image. And so depending on what you want that epsilon value to be. And so now EC, let's say size of E is about 1944. So midway is 1944 over 2. So let's say the midway, the 0 axis, positive frequencies are up here and negative frequencies are down here. And it's a real valued signal, so the eigenfunctions of an emission operator are real. If something's real, you're going to have, it's kind of irrelevant to look at the negative frequencies unless we had a complex valued signal to start with. So now, let's say EC is the crop value is E of, let's say 1 to 972, or I'll just say 1944 over 2 on a log scale here. Now we're just looking at the non-negative part of it. And you can see it chirps up and down and all over the place. And you can see this banding here, banding structure due to the fact that there's that there's a lot of harmonics, because the ECG signal is quite high, has a lot of high frequency content, a lot of harmonics. It's almost like a stream of Dirac delta measures, which will almost have this sort of Dirac-Coleman frequency space. So it reaches way out into the high frequencies. And now we can also sort of take a look at part of it. So I can say I can split it up even more. And if I say, okay, it's 972, let's just look at the inner part of it. Now we're kind of magnifying it up and looking into the part of it. And you can see here that you can definitely see the structure of it, where there's an initial upchirp right here. Right at this point, you can see it shoots up, and then it stays high, pretty high here. And then there's the swim, and then coming back, it's a lot lower coming back. So an interesting part here is kind of near the beginning, when we have laying down and then getting up and running. So the first little bit of it there is perhaps where it's quite interesting. So if we take that signal and look at the first part of it, so recall this part of it, the start part. So the part that has most of the chirp in it is roughly these 4,000 points here, has most of the chirpiness in it, CLF, and then plot ES. And then you can see it right here. You can see that there's quite a bit of this chirpiness going on here. You can see in these, 23, just over 20 heartbeats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 heartbeats there. It chirps from a fairly low frequency up to almost twice that frequency. So there's a lot of chirpiness in just that short little record. The short little chirp there, it's sort of hard to hear it. We can hear that. It might almost make sense to slow that down a little bit. Might make sense to slow that down just a hair. Let me comment this out and take this and make it something like, 5,000 samples per second or something. And then you can hear it there. Then you can hear that 5,000 samples. Starts slow and speeds up. Okay, so most of the interesting data from the chirp point of view is kind of in these 4,000 samples here. Yeah, what a beautiful day. The sun is setting soon. So now if we look at this data here, say S of, I've picked about 10,000 points or so where you can see let's clear off some of the dust off the screen here. It's almost beautiful the way the sun glints off the dust. It's beautiful. It reminds me of. So now let's say we take about 10,000 points of that sample. Now E equals TF of ES, and size of E is 141 square. So we can specify, we can override the default sizes and make it a little bit bigger. Let's make it say 2,000 high by 1,000 across, so that when we look at the positive frequency half of it, we got about 1,000 by 1,000. So let's go C of log of ABS of E plus some small epsilon, say 1, and you can see the pattern there. Now let's just look at the positive half of it, say 1 to 1,000. So that's just looking at the positive half of it. Maybe take it from 500 to 1,000. Just zooming in close to the origin there just a little bit, maybe even more. Say 750 to 1,000. So that's kind of 4 to 1. Now you can see the pattern there. You can see it's very nice the way it's chirping. You can see the chirping pattern there. It's quite beautiful to see. You can see it's definitely got a chirping characteristic to it. Now there's some DC offset in that signal, so if we subtract the mean, we can probably see it a little bit better. And then let's just display that again. And you can see it a little bit better there. If we subtract the mean off of it, pattern shows up a little bit more clearly. So you can see that chirping pattern there. If we come in a little bit closer to, there's about maybe 4,000 points right near where the center of the chirp is. If we come in a little bit closer to the 4,000 points or so, right centered where the chirp is, you can see we're kind of looking in closer to where the actual chirp signal is present. And now let's subtract the DC offset. Well, first, if we just look at the pattern as it is, we'll do the same thing, and then look at this, and we'll zoom way in, about 100 pixels, and you can see it kind of there. If I subtract the DC offset and do the same thing again and look at it, it's a little bit clearer, a little easier to see. You can see the pattern here. There's definitely this sort of sloping up. It starts at low frequencies at this end and higher frequencies at this end. You can see all the harmonics are increasing in frequency. So the fundamentals right chirping up, and of course all the harmonics are chirping with it. So they're all kind of going like this as you go progressively, so that whatever frequency this is, this is twice, 3 times, 4 times, 5 times, the same thing twice, 3 times, 4 times, 5 times at this end. So these are all kind of like straight lines that approximately. And so they're approximately fitting to what a Q chirplet would give you. Even though the days are getting longer, we're almost running out of sunlight here. So maybe I'll go up to the upper roof. If I go up to the top roof. So yeah, let's go up and enjoy that nice sunset. Beautiful. So with the Fourier Transform, we know we can use short-time Fourier Transform to analyze different kinds of signals. So this is a Doppler radar return from an iceberg fragment sort of bobbing up and down. These iceberg fragments are big enough to damage ships, but they're too small to show up in conventional radar, and that's where we used the chirplet transform to be able to see things that were invisible by other means. So it really saved a lot of collisions with these small iceberg fragments. And this is a typical iceberg fragment floating up and down, and it bobs up and down with the waves, so its Doppler shift is kind of a warble. So it almost looks sinusoidal in time frequency plane, because the frequency shifts like it's rising and falling in pitch. And so that simply means it's going up and down, actually in a circular motion. As the waves bob up and down, this iceberg fragment sort of swishes around in a circle almost, and so its Doppler shift is cyclic or periodic, and this is how the time frequency sliding window Fourier transform comes up. And now when we start to analyze it with chirplets, a chirplet is this form, e to the 2 pi I at plus bt plus ct squared, and so that it's got this quadratic in time in the exponential, and then we take the inner product of each of these chirplets with the signal under test, and so that gives us the kind of response. And we can use that Doppler. We use that often in wearables to see things. This is here we have the time frequency planes of various situations. This is a wearable computer with a backwards facing radar set that picks up, just at rest there's clutter, and then there's a car taking off at rest. Walking, we're sort of walking away, got negative frequencies there when you're walking away. Negative frequency from the ground clutter in a rear-facing radar. If there's a car hazard coming towards you, it looks like this. A pickpocket, there's a sudden movement towards you and then away. So we simulated kind of a pickpocket condition where somebody jumps up to you, grabs your wallet out of your back pocket and runs away, and that's what this pattern looks like. And then a stabbing motion. We didn't actually stab somebody, but we pretended to stab somebody. And so a person runs up behind you, and you get this Doppler shift, and then the knife comes forward and you get a higher Doppler shift. So we can kind of recognize, using machine learning, these various activities, like a car hazard, a car that's about to hit you, or a pickpocket, or someone who's about to stab you. So that those were kind of examples that we used with the chirplet transform, and you can see the chirplet signatures are unique here. These are the chirplet transforms of each of those conditions in terms of the beginning frequency and ending frequency of the frequency plane, and you can read more about that in the textbook. And so when we look at a typical signal from radar, for example, we've got the real and the imaginary radars, a complex signal, and the spectrogram here is very hard to see sometimes certain things, whereas the chirplet transform, we can see these immediate patterns in the signal that are otherwise maybe so weak that you can't see them by Fourier analysis. So we have here the radar clutter. This is the pickpocket signature, chirplet transform of the pickpocket. And then we also calibrated the radar using Koleski factorization. And this is all in the textbook, these simple examples of using radar system with the chirplet transform. And what we have, in a sense, is we've got this transform that is able to understand and capture, the signal of interest. So if we have, a Fourier transform, you're going to have something, the integral of e to the 2 pi I times time times frequency times some signal, say g of t dt, and that will take us into the frequency domain. It's going to give us a signal of frequency. And when you have, e to the 2 pi I times, let's say, some carrier frequency, fc specific frequency, times time, that's that's equal to cos 2 pi times the carrier frequency times time plus I times sine 2 pi times the carrier frequency times time, where I here is equal to the square root of -1. And so what we have is we've got this, the real part is the cosine and the imaginary part is the sine, and the magnitude is the square root of the sum of the squares of the real part and imaginary part, and the phase is the arctangent of the imaginary divided by the real. And so this is very familiar subject matter in electrical engineering, where we look at Fourier theory, and we try to do we look at it as a kind of an inner product. And you can think of it, if you think of it kind of as a matrix multiplication, you've got your Fourier transform. You can think of it as, you've got the DC component here, and then you've got, one cycle of a sine wave, and then you've got 2 cycles of a sine wave and a cos wave, real part and imaginary part. Real part is the cos wave, imaginary part is the sine wave, and then, 3 cycles, 4 cycles, and so on, and each of these is a higher and higher frequency, and we're kind of multiplying by the signal that we have here. If this signal was a vector, whatever your signal was, it might be an electrocardiogram signal, whatever it is. I'm just kind of drawing it sideways here, and we've got this matrix multiply, and where the first row of this matrix is just the all ones, so it's just the average of that signal, and that the DC component then is here in frequency, and then the next row is 1 cycle of a sine wave, inner product of 1 cycle of a sine wave with this thing, and then you get the next frequency component, then 2 cycles of a sine wave, next frequency component, 3 cycles of a sine wave, and so on. And so that's kind of what the Fourier transform in a sense does, is it's an inner product of the signal with a bunch of sine waves, and we might often write it like this, is this your signal, your transform of something, some waveform of t times your function g of t, and this is just 1, and then you've got a whole bunch of these, and you're taking an inner product with each of these waveforms. And so instead of having them be sines and cosines necessarily, what the chirplet transform does is it says that these can be chirps. So we can have a series of chirps. You might have a special case of a chirp is just a sine wave. A sine wave is a special case of a chirp. Even DC is a special case of a sine wave. A constant number is a special case of a sine wave where the frequency equals 0. Another special case is just a constant frequency. Another special case is, you can have up chirps and down chirps. So some of these chirps in this sort of, as we call, a dictionary of all possible chirps, some of them will be up chirps and some of them will be down chirps. And so you have every possible chirp within a certain parameterized space, taking the inner product, of this with the signal under test that we're trying to test to produce, some result in the output. And the way we parameterize that space is kind of really where the devil's in the details there. So if we take a typical parameterization that we often look at as beginning frequency and ending frequency. So F begin, and over here F sub end, let's say frequency of beginning and frequency of end. And so we may have negative frequencies of interest. Now if the signal's complex, we're interested in the positive and negative frequencies, but if it's not complex, we can't tell the difference between positive and negative frequencies, so we might only look at this one quadrant. More generally, of course, the chirplet transform frequency plane will have 0 at the origin. And if the starting frequency of the chirp is negative, possibly, and the ending frequency, we're over here, and if the ending frequency is negative, we're over here. So if it starts at negative frequencies and ends at negative frequencies, for example, we're over here, and we're right along the diagonal when the beginning frequency equals the ending frequency, and that's the Fourier transform. So the frequency plane of the chirplet transform, ff.m is the script that I wrote that computes this. And so if we're in this frequency plane, the diagonal is the Fourier transform. It's a slice through the chirplet transform. And of course the origin is the origin of the chirplet transform, which is just the DC offset, the average. And we might compute, I remember I went EG equals EG minus mean of EG, just to zero out the mean or remove the DC component, DC offset, because sometimes the DC offset will swamp this thing and make a huge peak at the origin and make it hard to see everything else. So a lot of times I like to just get rid of that origin, just blow away the origin, So many times I take the DC offset out. And now we're looking at the ECG, the electrocardiogram. Unlike the radar signals, you see the radar signals are complex, which is useful because then you can tell the difference between whether something's coming towards you and going away from you. You can tell the difference between positive and negative frequencies, which kind of means, whether you're going clockwise or counterclockwise around the argand plane. If this is your real axis and this is your imaginary axis, and when you can tell the difference between positive and negative frequencies, you're going clockwise or counterclockwise on the argand plane. And that's in certain situations with certain kinds of signals, such as radar, that's often useful. You can tell whether an object's coming towards the radar or away from the radar if the radar has a complex valued output. And so that's quite useful. In the case of the electrocardiogram, it's a real valued signal, so we only really need to consider in terms of the frequency spectrum, we only need to consider positive frequencies, so we can kind of get rid of the negative frequencies and not consider them. In case of the chirplet transform, it's in quadrants, so we only need to consider this quadrant here, and we can get rid of these other two quadrants and not bother with them. So here we have beginning frequency, ending frequency. Now, if we had a steady tone, it would fall somewhere on this line here. So it's going to be the Fourier transform. So if you had a low-pitched note, it would give you a strong return here. If you had a high-pitched note, it would give you a strong return over here somewhere. So you'd have, if you had a really low note, maybe there would be strong energy here, and if you had a higher note, it would give you a strong peak up here somewhere. This is a three-dimensional thing. The frequency plane has a height or a value, so it's going to be a three-dimensional context. And so that kind of gives you a general insight of what this frequency plane of the chirplet transform is going to give you. Now, if you have something that starts out at a low frequency, say it starts out at 0 hertz and it goes up to a high frequency. So if it starts out low, the starting frequency is going to be 0 on this axis. And then if it goes to a high frequency at the end, it's going to be here. So you have a strong peak here if you've got an upchirp that actually starts at 0. So more generally, upchirps are going to appear in this octant. I'll call this an octant because this is a quadrant, this whole thing. Negative frequency, so negative, positive, and negative, positive frequencies. But if we're only looking at positive frequencies, i.e. we have a real valued signal, then we're in this quadrant of the chirplet transform frequency plane. And if we're looking at up chirps, then we're in this octant over here. And if we're looking at down chirps, then we're in this octant over here. So now an up chirp that starts at 0 hertz and goes to some positive frequency is going to be right on this line here. And likewise, if the starting frequency is some high frequency and then it ends at 0, it's going to be on this line here. So these are up chirps here, like, and then down chirps, are over here. And if the down chirp goes all the way down to 0 at the end of the time window, it's going to be here. And we're considering f begin as the frequency at the beginning of the time window that we're considering, and f end is the frequency at the end of the time window that we're considering. So it's very simple to think of that in terms of octants and how it carves up the space on the chirplet transform. So when you compute the chirplet transform of this electrocardiogram, for example, you'll be able to see generally where that signal is. And so I hope that that's fun, and I hope you enjoy doing this assignment or lab or hackathon or whatever you want to call it. Thank you. It's getting a little windy. Time to call it a day.